So PES data, you have to remember that you know electron configuration already. So let's just go through. If you have sublevels, you have the number of orbitals in that sublevel, and then you have the number of electrons that can exist there. So we have S, P, D, and F. Numbers? 1, 3, 5, 7. JC doesn't understand.
I do, I think.
No, he doesn't understand. Should you do it for him?
No.
I think you should.
Yeah.
Let's go.
You'd be really good at it.
I'm good.
Why do I not understand?
I don't understand.
We had to cheer it. We had to cheer it until everybody said it. Don't you remember that?
I don't know.
We all cheered, and I wouldn't stop until the whole class
Henry
was
said he
cheering.
wanted to do it.
I said I didn't know what was going on.
So then we just remember SPDF 1357, SPDF 1357 over and over. So how many electrons can S hold? 2, 6, 10, and 14, right? And so let's just remember S is spherical, because we'll talk about this later. P is dumbbell, which is X, Y, and Z planes. D, which we didn't really talk about, but it does have more bells, and then it has like a loop in the middle, and then this one is a little bit more intense. So you know this, so you're going to use it to help you figure out what the graph is saying. So don't forget, like, you're not a brand new scientist to this. You don't have to figure out that all of a sudden there's subshells, because you already know there's subshells. You're just going to try to figure out which element it is on the periodic table. So we know that our rules are that electrons have to fill lowest energy sublevels first before they can go to the next one. So it's impossible to have 2 peaks on this unless the first one's completely filled. Do you agree? So each peak represents a new sublevel that is existing. If there's a new peak, it means all the ones before it are filled already. So this is obviously our first peak in 1s, and there's only one of them. This was 1s2, we said. Now I have 2 peaks. I know that what comes after 1s? 2s. So this must be 1s2 because it's filled, and now this is half the height, so this must be 2s1. Then there's 2 peaks again. So this must be 1s2, this must be 2s. It's the same height as that one, so that must be 2s2. Now I have 3 peaks. You know that S can only hold 2, right? So that third peak, what comes after 2s? 2p. And since this is already filled, this is half that height, this must be 1s2, 2s2, 2p1. So you can figure out what the elements are just by looking at the peaks. All right, so let's go to the next one. I'm going to kind of hide these, even though you can see them, but just kind of when you're looking up here, we're going to pretend like this is the exam where you're not going to be given which element it is, you have to figure it out. So by just looking at the graph, from the first one, I can say I have 3 peaks. So how many sublevels do I have? 3 sublevels. Every peak represents a sublevel, right? And what they didn't understand is that there were, in fact, sublevels. They just thought there was energy level 1, energy level 2, energy level 3. And then this information provided the fact that there were sublevels existing. So we would have expected, if everything was in energy level 2, we said energy level 2 can hold 8 electrons, correct? So if there weren't sublevels, this peak should eventually be the height of 8. Do you follow that? But since all of a sudden we saw a peak, this only holding 2, and then this peak starts forming, that's how they realized that sublevels do in fact exist. Because if it can hold 8, then this one should be filled with 8. Do you get that? Anna? No. Well, how many electrons can n equals 2 hold? All of 2 can hold 8, right? So pretend you don't understand that there's sublevels existing, and you just think there should be 8 electrons. Then you would have expected, if we're at, this one is carbon, if we're at carbon, we should have expected to see this, 1s2, and then I should have expected to see this being 2s4, if sublevels didn't exist. But because they exist, all of a sudden, I see a new peak, and I'm like, well, I know that electrons have to fill lowest energy levels first, so this must be at a different energy level than this one. And so then I know that this must mean that this is 1s2, This must be 2s2, and now, oh, there's a sublevel in 2 that I didn't know about. That's what PES Data told them. So that's 2p2.
How do you know it's 2p?
Because I know, and so do you, what comes after s.
I know it comes after, but why isn't it like 2p3 or 2p?
Yes.
Because the peak height is the same as all the others.
It's the same. So like.
Oh, so if it's the same as one of the S's, then it has to be 2.
Yes. So this is what you're going to do, because that part will get tricky, because you're not going to be able to compare it going down a line. Like this, you just know the next one's 3, and the next one's 4, and the next one's 5.
So they're not going to be in order.
It's not going to be in order. You're going to get one of them. So what I would do if I were you is I would get a ruler out and actually measure them. So on your homework or on the exam or the AP test, you might want to take like your pencil and kind of estimate where those measurements are so that you can come up with the correct peak height. Kirsten.
But for like the second one and third one, it looks like the third one, the last peak is taller, but then it says 1.31.
That's the energy. So remember megajoules per mole? It has less ionization energy because it's further from the nucleus. That doesn't have anything to do with the peak height. So then these are 1s2. I have 3 peaks. So this must be 2s2, and then this must be 2p, just a little bit higher, 3.
So if you have 2 peaks, then you always know there has to be 2s1.
You have 2 peaks?
If you have like the first one and then like the second one, it just stops. It's always 2s1.
It could be 2s2.
But how do you know?
Peak height. If it were 2s1, it would go back to the slide before. You would have seen it. You would see what it looks like. It's half the height of the first peak. All right, so then this third one, this is double the height of this peak. I have 3 peaks, so that means I have how many sublevels? 3 sublevels. They're going to be 1s, 2s, and 2p. And now I'm going to look at the peak height to determine what that last one is. So that's double the amount of this, so that's 2p4. Now these, I would say, if I just gave you this one slide here, that'd be really tricky for you to do, because just visually you might be like, oh, it's double that. But I would get a ruler out and measure it just to be sure, okay? So again, 3 peaks, 3 sublevels, 1s2, 2s2, and this one is 2p5, this one's 2p6. Following?
Yeah.
All right, so take your homework, flip to the number. Here it is. So look at number 11. So in your notes or directly on your homework, I don't know where you do your homework, but we're going to try this. So you're going to draw what the PES data should look like for aluminum. So you're not going to include exact ionization energies because we don't know what they are. You're just going to draw a general graph like this and just show some peaks. So everybody try that on your own. Let me just video this so that way if anybody's watching it. So for aluminum, here's how you think about this. You should know, and I'll go over today, electron configurations, just how to read it from the periodic table, but you know that aluminum ends up in a 3p1. So if that's true, then you have to have 1s filled, 2s filled, 2p filled, 3s filled, and now 3p partially filled. So I have 5 sublevels, so I'm going to have 5 peaks for sure, right? And if I fill them, I should have one with a peak height that matches this peak height. That's 1s, that's 2s. Then I have 2p6. I don't know, something like that. And then after that, I'm in the 3s2, so same peak height as that. And now this one is a 1er. So you should make sure that it looks like it's half the height of these peaks, right? And then obviously this is roughly 6, but it doesn't even matter if it's roughly not 6 or 5. The fact that this peak exists means this one's full.
Oh, okay.
Okay? So the next part says, label each peak with numbers and letters that indicate its associated shell and subshell. If you can't follow directions on the exam, you're going to get points off. So follow these directions, and then I'll tell you if you followed them correctly. All right, did you do this? Oops.
Is that wrong?
That's wrong.
Ah.
You need to
what did the directions ask you to do?
And indicates associated.
Just put the number and the letter. It said just put the shell and the subshell. So if you can't follow directions, I'm going to take points off. Okay?
If we put it underneath, is that okay?
That's fine, yeah. And honestly, on a lot of the exams, they're not going to ask you to label diagrams. They're just going to ask you questions, and you're going to write them in the free response section where it's located. All right, the next one says indicate the number of electrons that are contained within each subshell. So now you're going to write the number of electrons that are contained there. So 2 electrons, 2 electrons, 6 electrons, 2 electrons, 1 electron. I'm just being specific because these are the directions. It's not necessarily what you're going to get on my exam or on the AP exam. It's just I'm trying to train you to do what the question asks and not what you want to do. And sometimes questions are going to give you facts or statements that you don't necessarily agree with, but you still have to make it work. You still have to figure out a way to answer what they're telling you. And then the last one, letter D, which subshell contains the electron with the lowest ionization energy, and then justify. So you don't need to write this down, but discuss with your group and justify. You should have a good answer.
According to the shell.
Okay, so this is just saying what I wrote on the board before about how many electrons can be held in the sublevels, so we can skip this. And then here is some ionization energy data that's just meant to kind of help you see the general dipping trend here. So when you looked at that chart, you can see that if you're going across, maybe like this way, or maybe you can see it on this one, but mostly from here to here. When you go from magnesium to aluminum, our expectation is to go up that graph, but we actually dip once we hit that 3P due to shielding. All right, so this is shielding effect within a shell. So we have shielding amongst shells, but then within a shell it says an electron in 2s spends more of its time further from the nucleus than one in 2p. But the electron density near the nucleus is greater for 2s electrons due to the first maximum, which is partly due to that shielding. And the addition, sorry, not the shielding, the addition of additional sublevels in that level is pushing that a little bit closer, thank you, yep, pushing it a little bit closer to the nucleus. So here is where shape will help you. If you think of S as a sphere and P as the dumbbell, and these are within those orbitals, and we're thinking here's our nucleus and here's energy level 1 and energy level 2, sphere and dumbbell, you can kind of see what this is saying. An electron in 2s spends more of its time further from the nucleus. That's because the sphere itself is not providing the proximity to the nucleus. Plus, this D block, you can think of it like this, 3s, 3p, I'm sorry, not D, but 3p perhaps, is pushing this one also. So its proximity, it says, is less often from close to the nucleus, and then the 1 and 2p. But the electron density is near the nucleus is greater because it just has less space to travel than the p. This is definitely way more complex than what the AP exam will ever ask you. It's just trying to show you that within a sublevel, there's shielding from those other sublevels, from the other orbitals. So 2p electrons experience a greater shielding effect from the 1s electrons than do the 2s electrons. And we'll do this again in lecture 3. We'll talk about shielding within a shell. But it's not really, it will not be asked of you on the AP exam. Just general shielding questions will be asked overall. I don't really go into shielding within the shell because it is more complicated, and honestly, like your multiple choice questions, they usually just want to know that you understand Coulomb's law and shielding. So it might have like a multiple choice question, and then it's partly, thank you again, partly, it'll just say force of attraction and distance, and then it'll say force of attraction, distance, and shielding, and then you realize that the answer is also shielding. Thank you. Oh, she's not here.
Okay.
All right, so this one is showing you distance from the nucleus and then radial probability. And this radial probability is sort of like where these radiate. You can think of it that way. So in all shells, electrons electron density near the nucleus decreases with each subsequent subshell that is added. So more subshells, 3s, but then I add 3p and then I add 3d, causes the electron density near the nucleus to decrease. Thus, the shielding effect increases for each subshell that is added. Make sense? So within a shell, you add more orbitals or subshells, you create more shielding within there.
Like D is the most
So here's a summary of that. So this is the distance to the nucleus. And it is what you think it should be. It's not, it doesn't really deviate from that. The ionization energy for 3s is greater than the ionization energy for 3p and greater than the ionization energy for 3d. Okay, so it says, although the average distance between the nucleus and electrons decreases as subsequent subshells are added within a shell, the ionization energy decreases due to an increase in the shielding effect. So, yes, we're moving further from the nucleus, which we would anticipate that the ionization energy should decrease because we're moving further away. But what they're trying to make you understand is within a subshell, it's really due to that shielding effect than necessarily just Coulomb's law. Okay? I think that's the end of this lecture. So come up and get atomic theory 3. So we have orbitals we're going to discuss, which you know already. We are going to quickly review electron configurations, noble gas configurations. That's all we're going to get to today. And then on Monday, we'll go through all the trends. So the trends, you guys are going to be really good at because I made my honors class answer AP questions on their test. So you will remember this because I'll say, like, which atom is larger and why. So you guys had to justify it, whereas JC, you may have just had to say, which atom is larger? Oh, it's because it's on the left side of the periodic table.
We literally, he gave us the trends on a piece of paper that we used on the test.
Okay.
So I need to stay after school on Monday and like go
No,
over the
I'm
trends.
going to teach it to you on Monday.
Okay.
Yeah. We're all going to go over it again. I said I don't expect you to remember this stuff from honors. For some of you, it's a year ago. So I will go over all of it again. If as I'm going over something you don't understand it, then you're going to stay after. But I'm going to kind of review this. Keep going to the wrong laptop. All right, the Bohr and the shell models. Bohr model is your Jimmy Neutron model. Looks like this one. So we think of these electrons that are on this roller coaster ride and they're just staying there. And you can sort of think of that as electrons anyway, even though we're not using the Bohr model anymore, because we do have to sort of say they're in this level and then they jump away from this level and come back to this level. But we advance this to the probability model, which is called the quantum mechanical model. So we say that electrons have a probability of residing in this space around the nucleus most of the time. And then in this space most of the time. So we create these sort of cloudy regions of where electrons could possibly reside. So I use this sort of like as a GPS location. Remember I was saying we're trying to find where we are. So we're in the United States, we're in New Jersey, we're in Brick, we're on Lanes Mill Road, we're in Brick Memorial High School, room 236, but once we get here, you guys could be in this area anywhere. I don't know your exact location, and one of you might have left to go to the bathroom. So like this is 90% probability of finding one of you at this moment in here. Get it? Okay. So that's what this says. Bohr's equation that predicted the energy levels of orbits only worked for hydrogen, but then we realized if we don't just have n equals 1, 2, 3, 4, 5 like this, we have in fact sublevels, and that's what PES Data showed. So the solution for this model is we must have this probability model, the quantum mechanical model. So it says electrons do not follow orbits. A wave function describes the electron's possible positions in three-dimensional space. It's often called an orbital. And then we have all of these. And it just says that last bullet there is that every electron that exists in that sublevel has the same exact quantized energy. So if 6 of us reside in 2p6, we all have the same quantized energy. So an orbital is a graphic representation of the space that an electron will occupy 90% of the time. It is a concept and not a physical structure. It's just this is the cloudy region of where we expect electrons to be. So here's where the electrons could be, and then we put a little circle around them, and we say 90% of the time, they go underneath that tissue box in that folder. 90% of the time, they are found in this location, just like I said about you guys being in this room. And so yeah, and this is where the electrons are. That was for an s orbital. So now if we go to a p orbital, p is dumbbell shaped, right? P can reside in the x, y, and z plane. This is the x plane because it's horizontal. Then we can reside in the y plane because it's vertical. And then the z plane is the 3D plane that's coming out at you. So if you look at this, you can think of this yellow circle coming out at you, and then the back of it is going into O'Donnell's room, and then the x coming across the board and the y going up and down the board. All right, we're going to go over some basic rules for electron configuration. You always add electrons to the lowest energy level first. This is what we were saying for PES. If we have a second peak, we know the first one's already filled because you can't go to the next energy level unless you filled the first one. Nature always favors a low energy system, and then we can follow a format to do that. So caveat here. You will see occasionally orbitals that are not filled, and the next one is starting to be filled. So in particular, for example, chromium will do this. So chromium, we expect, if we do a noble gas shortcut, I'll show you noble gas shortcut in a minute, but we would expect 4s2, 3d4. But in fact, that doesn't happen. What we end up with is 4s1, 3d5. Does anybody remember why? Huh? But what's the reason why it does it? It's less energy. Because atoms prefer partially half-filled orbitals instead of partially filled orbitals. So this is partially filled. This is half-filled, half-filled. Half-filled, half-filled is a lower energy state than partially and full. So you don't have to predict that stuff. You should just know that that does in fact happen. They may show you an example, and the reason is because it's at a lower energy system. And nature always favors low energy systems. All right, so let's recall how we do this by looking at the periodic table. So first thing is that this is your S block, this is your P block, D block, and F block. In the D block, you subtract 1 from the period number, right? The period number tells you the energy level. You subtract 1 from the period number when you enter the D block. For the F block, you subtract 2 from the period number to get you your energy level. And then your blocks indicate the number of electrons. So you can see from this slide, you go 5s2 and then to 4d1. When you get down to the 6th and 7th period, you have to remember to go into the F block, which is a little tricky because some periodic tables like this one make you believe that the lanthanide, that element, lanthanum, that one, it makes you believe that you're actually into the F block already, but in fact, that one is the first of the D block. So you come out of the S block and you go into the F block, and then back up to the D block. So that's what this is showing you here, that these are your 4F as soon as you come out to 4F14, and then you go back up to 5D1. But 5D1 is LA, and 6D1 is AC. Yeah, AC. Okay? So how many of you remember how to read it like a book? Anybody not remember how to read it like a book? That's probably the better question to ask.
It's like a book just like straight across.
Yeah, like you just, if I'm saying, and I can do it now, if I'm saying nickel, then I'm going to read 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then down to 3d, 1, 2, 3, 4, 5, 6, 7, 8, 3d8. Do you remember that? Okay. Yep.
Oh, never mind.
Okay. So this is ridiculous, these slides, so let's just quickly look at them. Hydrogen's 1s1, helium's 1s2, lithium is 1s2 or 2s1. What's that thing called when it's in brackets? The noble gas shortcut. So on your homework, you'll see it says you can use the shorthand method. Shorthand means use the noble gas shortcut. So the noble gas shortcut means that you put the noble gas prior to the element of interest in brackets, and you're basically saying, this is all the configuration stored up in here. If you're doing a noble gas shortcut of a noble gas, you still just go to the noble gas prior to it and then finish the electron configuration. Beryllium, here are some other fillings. You can see them there. All right, and then this one helps you recognize how the F block works. So it's asking you to take a look at samarium, which is SM. That's in the F block. So here are all your configurations. We get to 6s2, so you're in period 6, and then you hop out and you go to 4f5, which will give you SM. Notice that you didn't go to like 5d1 first to hit lanthanum. You didn't, you went down to the F block and then you'll come back up. Yep?
So the thing that you were saying about the partially filled and the half filled, like if it was the one before samarium and it was 4f4, would you rate 6s1?
No, you're not, because there are tables to tell you who does it and what, like certain ones do it. I don't have those memorized. I know for sure that chromium does. The expectation is that if you get one of them, if you're given a configuration or you see something that looks odd, that you would know the reason for it. They're not going to ask you, nor would I, to predict every single time that you might have to move an electron to make it partially filled and so forth.
It would kind of be like a multiple question, like this is the configuration.
Yes.
What is it?
Why? Yeah. What is it is a good example. Why does this occur? That's another one. But not like every time you write a configuration, you have to ask yourself, is it partially full? Should I move this one? You don't have to do that. Because that doesn't happen for all of them. All right, so rules for filling. You know these. Aufbau's principle and Hund's principle. In years past, these have been on the AP exam as like a matching question. While I would hope they don't do that anymore because the curriculum is changed so that it's a little bit harder than just basic memorization, it's possible that you will get questions, even from me, because I have to keep track of what the AP exam is doing, that I ask you to do something and then I'll say, whose rule is this? So just make sure you know whose rules things are, just in case. So each orbital can hold a max of 2 electrons, and that's with a spin up, spin down. So I'm going to, not part of our curriculum, I'm just going to let you know so that when you get to college, and if you do retake this course, there are things beyond AP chemistry that your professors might teach you. So I have gotten messages in the past, not everything is all about SPDF, which is funny because I make you guys cheer SPDF. And the reason why she had sent me that message is because her professor was teaching on M's, L's, and +1/2 and -1/2, which are things that you do for electron configuration. It's just kind of giving more of that GPS location. So there's stuff beyond this, but we don't need to know it all for this curriculum. Like +1/2, -1/2 is just a different way of saying clockwise and counterclockwise spinning. So it would just, so you can kind of see if I have a +1/2 and a -1/2, they cancel each other out. But we're just going to stick with clockwise and counterclockwise, okay? There's a little bit beyond this. Number 2, when you have more than one orbital in a subshell, P, D, and F, a single spin-up electron is added to each orbital before starting to add spin-downs. So that's what this means. 3p, 3p, 3p. If I have 4 electrons, I go 1, 2, 3, then 4, right? So that would be correct for lithium, because lithium is 3 electrons. That would be correct for fluorine. It has 5 electrons in its outermost energy level. But this is not correct for nitrogen. What's wrong with this? It should just have 3 going up, right? You place 1 paired electron in each of those energy levels. They're all of the same energy, same quantized energy with the same spin, and this creates the lower energy system. All right, so these are now 2 new words that you have to memorize, and it's just basically saying like how many paired and how many unpaired are there. Those were the words that we would have used in honors chem. Now we're going to use paramagnetic and diamagnetic. So di means 2, which means they would be paired. Para would mean that there's only one of them. So if something is paramagnetic, it means that they have unpaired electrons. Any number of unpaired electrons creates a paramagnetic moment. And what this means is that if you put a magnetic field up and you send these atoms through, these would be attracted to a magnetic field because there's a charge related to it. because there's that plus 1/2, plus 1/2, plus 1/2, and not until they all come paired with a minus 1/2 will they actually become neutral and not be attracted to a magnetic field. So this one is carbon. Carbon only has 2 electrons in its outermost energy level. They're both spin up, so it creates a paramagnetic moment. So you will be asked to explain those, and the questions will usually say, blah, 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 is it attracted to a magnetic field? Justify your answer.
So if it's paramagnetic, it's attracted to the field. If it's diamagnetic, it's
Right. So here's diamagnetic. Lone atoms with no unpaired electrons are not attracted by magnetic fields as the individual magnetic moments cancel when the electrons are paired. So plus 1/2 minus 1/2 cancels. And so you can see just by doing it that there's no unpaired electrons. So how do you answer questions related to that? I would draw out the outermost electron configuration. You don't have to do all of them, but I would draw this out, the outer part. Just see if there's paired or unpaired. And then you would be able to answer if it's paramagnetic or diamagnetic. And then you could answer if it's attracted to a magnetic field or not. Yes?
So even if it just has one unpaired
Yep.
thing, the whole
Yes.
atom is magnetic.
Yep. All right, here's a little bit more about shielding. So can you read this on your own so I don't have to read everything out loud? Anything new here? Nope. This is really what you're expected to know. I would not worry about like shielding within the subshell sort of stuff, but definitely understanding shielding within the energy levels and understanding that those repulsive forces even create more shielding effect. All right, effective nuclear charge. So I've used this term frequently with you, but there is an actual equation for it. We will not use it. The point of the equation being up here is so that you can see this is the charge experienced by an electron, this is the actual nuclear charge, the atomic number of the element, and then this is a shielding constant, which would be a number specifically for that atom. So you'll see that you have to actually subtract that out in order to get the actual charge. It says repulsive forces caused by the shielding effect reduce the effective nuclear charge experienced by quarter electrons. So it's just that it's present. Shielding does reduce force of attraction. All right, periodicity. Predictable physical and chemical trends that occur as one moves across a period or down a group in the periodic table. We will examine atomic radii, ionic radii, ionization energies, and electronegativity. The only one that's not up here is electron affinity, but electron affinity is very much the same as electronegativity. It's just within an atom versus within an atom to another atom, so in a molecule. But they're still very much the same. So when you are writing your justifications for this, it is so important that you tie it all in with your therefore statement to whatever it is you're explaining. Do you understand? You can't just talk about Coulomb's law, talk about shielding, and talk about effective nuclear charge, and then stop. It has to be related to whatever the question's asking you to find or discuss. All right, let's do atomic radius, and then we'll stop. The general trend for atomic radius is this. You know I like my arrows to all point in the same direction, right? So this means that this is the largest. That just looks confusing, doesn't it? So fix it. So that when you go back to study it, you're not like, oh, I thought the arrows went the same way. So the largest atom would be what? Kara? Francium. All right, so why is it the largest? Tell your group. Why is francium the largest?
the only one I ever understood. Yeah, that was
Yeah, atomic radii, Kristen, you're saying this is the only one that I was good at, but atomic radii really has to relate all of them, because the size in effective nuclear charge then helps you figure out all the others. So luckily for you in your notes, it's giving you written out instructions on how to answer group trend and period trend, which you need to answer both of them when you're trying to justify your answers. So, down a group from top to bottom. So starting at the top of the periodic table, moving down. New shells are added, which means the principal quantum number increases. Principal quantum number, just to remind you, is the N equals. This is your energy level, that's what that means, energy level. Valence electrons have more energy, are less stable, and are further from the nucleus. The outer electrons experience a greater shielding effect and a decreased effective nuclear charge. And according to Coulomb's law, the force of attraction decreases as the distance between the electrons and the protons increases. So truly, this is the reason why going down a group. This is discussing stuff that we're going to get to later. But going down a group, more energy levels are added, more orbitals are added, and therefore it's further from the nucleus. So it's distance, meaning it's the largest. Then you have your period trend from left to right. So this is that effective nuclear charge. Period trends are always effective nuclear charge. Group trends are always going to be related to distance from the nucleus because of energy levels being added, like a ladder. So going from left to right, we're increasing the number of protons in that energy level. Therefore, effective nuclear charge increases because charge is increasing in Coulomb's law, right? And if charge increases, then force of attraction to the nucleus increases. And so our atom then shrinks because it's drawing those energy levels in closer to the nucleus. So it says valence electrons are all in the same shell, aren't they? So we're comparing the shell. Don't think of it as individual electrons. The shielding effect experienced by the outer electrons of the elements in a period will be similar to the addition of protons increasing the effective nuclear charge on those electrons. Because sometimes you guys will think then there's shielding occurring. Why isn't it actually the effective nuclear charge not going down? But it's because protons are increasing and we're looking at Q. So this is going up. So the force of attraction is increasing. Moving from left to right, more protons are added. According to Coulomb's law, the increase in positive charge increases the force of attraction experienced by each electron, thereby decreasing the radius. So it's like a magnet sucking it in, getting it closer and closer. So therefore, things on the right have smaller radii than things on the left. We remember this?